Tonight, we are going to explore the true size of the universe. Not the simplified version you were taught in school. Not the neat, colorful diagrams found in the comforting pages of high school textbooks, but the actual, raw scale of reality as modern astrophysics and observational cosmology understand it. We are stepping into a cosmos so vast that light itself, the absolute speed limit of our universe, still requires billions of years to cross even small, arbitrary fractions of it. We are confronting a reality filled with structures so completely gargantuan that entire galaxies, containing hundreds of billions of worlds, become nothing more than microscopic, dust-like components inside colossal cosmic webs that stretch across the dark fabric of space-time for tens of billions of light-years. By the time our journey concludes tonight, you may begin to experience a deeply unsettling, yet profoundly beautiful realization: the observable universe, everything humanity can currently see, detect, map, and analyze with our most advanced space telescopes, is not the universe itself. It may only be an infinitesimally tiny, microscopic fragment of what truly exists. Because beyond the cosmic horizon, beyond the boundary where light has had time to reach us since the dawn of time, reality may simply continue, forever. But before we leap into the infinite, we must look backward. We must understand how we arrived at this terrifyingly vast modern vantage point. For almost the entirety of human history, humanity believed the universe was small, intimate, and designed explicitly for us. Ancient civilizations looked up at the night sky and saw a dome. To the Babylonians, the Egyptians, and the early Greeks, the earth was a flat or spherical anchor fixed immovably at the literal center of existence. The stars were not roaring furnaces of nuclear fusion separated by trillions of kilometers of vacuum. They were merely brilliant little lights, pinpricks of celestial fire attached to a physical, rotating sphere that encapsulated the world. Space did not extend onward into an abyss. It had a ceiling. It had a physical boundary just beyond the high clouds. Even as the centuries turned and the scientific revolution of Copernicus, Galileo, and Newton shattered the geocentric model, placing the sun at the center of our solar system, our conceptual prison remained remarkably small. The sun became just one star among many, yes, but those stars were still believed to reside within a solitary, self-contained system. As recently as the early 20th century, barely a single human lifespan ago, the world's leading astronomers were locked in a fierce, unresolved debate regarding the ultimate boundary of reality. This historical turning point, formalized in 1920 as the Great Debate between Harlow Shapley and Heber Curtis, asked a fundamental question: was the Milky Way galaxy the entirety of the universe, or were there things that lay beyond its borders? Think about the psychological reality of that moment. Every single visible star you can see with the naked eye on the clearest, darkest night on Earth. Every swirling, ghostly nebula captured by early photographic plates. Every glowing, majestic object tracked by the world's most powerful observatories. Everything humanity had ever cataloged in the heavens was believed to exist inside one solitary, cosmic island, our own galaxy. Beyond the outer fringes of the Milky Way, astronomers imagined nothing but an eternal, empty, featureless void that extended into a meaningless infinity. The universe was synonymous with the Milky Way. And then, in a single stroke of observational genius, the universe burst its banks. Chapter 2: The Night the Sky Opened. In the mid-1920s, a quiet, meticulous astronomer named Edwin Hubble climbed up to the high, cold summit of Mount Wilson in California. He was working with the Hooker telescope, a magnificent 100-inch reflector that was, at the time, the largest and most powerful optical instrument ever constructed by human hands. Hubble turned the telescope toward a faint, smudged, spiral-shaped patch of light in the constellation Andromeda. At the time, the orthodox astronomical community referred to these faint, ghostly shapes as spiral nebulae. The prevailing consensus was that they were merely localized, swirling clouds of interstellar gas and dust located well within the boundaries of the Milky Way, perhaps new solar systems in the painful, protracted process of birthing planets. But Hubble noticed something unusual in the outer spiral arms of the Andromeda Nebula. It was a tiny, fluctuating point of light, a specific type of star known as a Cepheid variable. To understand why this discovery changed human history, we must understand the mechanics of a Cepheid variable. Discovered by Henrietta Swan Leavitt in the early 20th century, these extraordinary stars act as the standard candles of the cosmos. Cepheid variables possess a unique, intrinsic physical property. Their actual, intrinsic brightness is directly, mathematically linked to the precise rate at which they pulse. They blink with absolute, mathematical predictability. By measuring the exact time it takes for a Cepheid variable to go from bright to dim and back to bright again, an astronomer can calculate exactly how much raw light that star is actually pumping out into space. Once you know how intrinsically bright a star truly is, and you compare that to how dim it appears through your telescope, the laws of physics allow you to calculate its exact distance with astonishing precision. It is the cosmic equivalent of looking at a distant car headlight on a dark highway. If you know the wattage of the bulb, you can tell exactly how many kilometers away the car is based entirely on how faint its light appears. Hubble meticulously photographed the Andromeda Cepheid night after night, comparing the plates, measuring its period of variability. When he finally computed the mathematical equations, the numbers that stared back at him from his notepad did not make sense within the context of early 20th century astronomy. The star was not a few hundred light-years away. It was not a few thousand light-years away. It was calculated to be more than 2 million light-years distant from Earth. The implications hit the scientific community like a seismic shockwave. The Andromeda Nebula was not a cloud of gas inside the Milky Way. It could not be. The Milky Way itself was far too small to contain something at that staggering distance. Andromeda was an entirely separate, autonomous, colossal island of stars located deep within an unmapped abyss of intergalactic space. Overnight, the architectural blueprint of reality was torn to shreds and redrawn. The Milky Way was no longer the undisputed boundary of the universe. It was suddenly reduced to a lonely, singular cosmic citizen, just one galaxy among a multitude of others. The cosmic horizon had ruptured, and humanity's understanding of the scale of reality expanded by orders of magnitude overnight. The architecture of the macrocosm, Chapter 3, the galactic census today, with our modern fleet of space-based observatories like Hubble, James Webb, and Gaia, we look back at the anxieties of 1920 with a sense of profound awe. We now know that the universe does not merely contain a few dozen or a few hundred of these external galaxies. Astronomers modernly estimate that there are roughly 2 trillion galaxies contained inside the volume of our observable universe alone. Let that number sit heavily in your mind for a moment. Think not of individual stars, planets, or moons. Think of an entire galaxy, a swirling, majestic metropolis of matter containing hundreds of billions of suns, millions of planetary systems, vast stellar nurseries, and massive black holes. Now, imagine 2 trillion of those distinct structures scattered across the void. If you were to count every single galaxy in the observable universe out loud at a rate of 1 galaxy per second, without ever stopping to sleep, eat, or breathe, many galaxies contain hundreds of billions of individual stars. Some of the largest giant elliptical galaxies we have discovered contain upwards of 10 trillion stars orbiting within their colossal gravitational wells. The sheer arithmetic of the cosmos quickly detaches itself from our evolutionary intuition. Our brains simply did not evolve on the African savanna to emotionally process numbers of this magnitude. Consider our own home, the Milky Way. It is a barred spiral galaxy, a majestic, cosmic pinwheel of gas, dust, and stellar systems. Modern estimates suggest it contains somewhere between 100 billion and 400 billion individual stars. Our Sun is just one ordinary, middle-aged star nestled quietly in the inner edge of the Orion Cygnus arm, located roughly 26,000 light-years away from the hypermassive black hole that rules the galactic center. To understand the physical scale of this home galaxy, we must look at its dimensions. The Milky Way is approximately 100,000 light-years across. If you could somehow board a spacecraft that could travel at the speed of light every single second, and you flipped the switch to blast off from the absolute leftmost edge of the galactic disk, it would take you 100,000 years of continuous, unbroken travel just to reach the opposite side. Entire human civilizations would rise, flourish, fall to dust, and be forgotten by history while you were still making your way through the local neighborhood of our single galaxy. Yet, within the grand cosmic census, the Milky Way is thoroughly average. It is a medium-sized galaxy. The universe plays host to structures that make our home look like a microscopic speck. On the smaller end of the spectrum, there are dwarf galaxies, fragile stellar collections containing a few million to a few billion stars. But on the upper end lie the monsters of the deep cosmos. Consider the galaxy known as IC 1101. Located over 1 billion light-years away in the Abell 2029 galaxy cluster, IC 1101 is one of the largest single galaxies ever discovered in the known universe. It is a gargantuan, swollen elliptical galaxy that stretches nearly 4 million light-years. IC 1101 is roughly 40 times wider than the entire Milky Way. If you replaced the Milky Way with IC 1101 in our local neighborhood, it would completely swallow up the space between us and the Andromeda galaxy, devouring our nearest neighbors and enveloping multiple surrounding galaxies within its own colossal, glowing boundary. It contains an estimated 100 trillion stars. It is a cosmic behemoth, an island universe of such mind-numbing proportions that light itself requires millions of years just to traverse its diameter. Inside these galaxies are solar systems. Inside those solar systems are planets. And on one small, fragile, rocky world orbiting an ordinary yellow dwarf star, biological consciousness emerged. From our microscopic perspective on this planet, the scale of our immediate surroundings already feels completely overwhelming. But the truth is, we are still standing on the shore of an impossibly deep ocean. We are only getting started. The local neighborhood. To truly understand how deep this ocean goes, we must zoom in on our immediate galactic neighborhood and look at the terrifying amounts of empty space that separate these islands of matter. The closest star system to our planet Earth is Alpha Centauri. It is a triple star system located roughly 4.37 light-years away from us. When you walk outside at night and look up at Alpha Centauri, the photons of light striking your retina tonight did not leave that star an hour ago, or yesterday, or even last month. They began their journey through the cold vacuum of space more than 4 years ago. Those photons have been racing through the void at 300,000 kilometers per second since before the major global historical events of recent years even began. You are not looking at Alpha Centauri as it exists now. You are looking at a ghost of its past that if humanity were to launch our fastest current interstellar spacecraft such as the Voyager 1 probe, which is currently screaming out of our solar system at roughly 61,000 kilometers per hour, it would still take that human artifact more than $70,000 text years dollar to reach our closest stellar neighbor. And remember, Alpha Centauri is our immediate next-door neighbor. It is the closest house on our cosmic street. The Milky Way contains hundreds of billions of other stars, and almost all of them are separated by these same vast, unbridgeable oceans of mostly empty space. On average, stars in our region of the galaxy are separated by distances measured in trillions of kilometers. Space, as it turns out, is mostly just an incredibly vast emptiness. Even our own solar system is vastly larger than the common textbook illustration suggests. We often see diagrams where the planets are lined up neatly next to the Sun, all fitting comfortably on a single page. This is a complete fiction dictated by the limits of printing paper. In reality, if you travel past the orbit of Neptune, past the icy, dark world of Pluto and the Kuiper Belt, you would eventually encounter the true outer boundary of the Sun's gravitational domain, the Oort cloud. The Oort cloud is an immense, thick spherical shell composed of trillions of icy, rocky objects, serving as the distant repository from which long-period comets emerge. The inner edge of this cold, silent shell begins thousands of times farther out than the distance from the Earth to the Sun. Its absolute outer edge is estimated to extend nearly 2 light-years into the dark void, almost halfway to Alpha Centauri itself. It takes light from our own Sun nearly 2 full years of continuous travel just to reach the absolute boundary of our own solar system's backyard. Our planetary home is not a compact little neighborhood. It is an incredibly sparse, isolated system adrift in a stellar desert. And if you leave the outer edge of the Oort cloud behind, you enter the true abyss, intergalactic space. The distance between galaxies is even more difficult to comprehend than the distance between stars. Our nearest major galactic neighbor is the Andromeda Galaxy, designated by astronomers as M31. It sits roughly 2.5 million light-years away from Earth. The light we see from Andromeda tonight left that galaxy at a time when early human ancestors were just beginning to walk the Earth and fashion the crudest stone tools. Andromeda is not stationary. It is currently locked in a gravitational dance with the Milky Way, falling toward us through the dark at approximately 110 kilometers per second. In about 4.5 billion years, our two galaxies will inevitably collide. But because galaxies are composed mostly of empty space, this will not be a cataclysmic explosion of stars smashing into stars. If you were standing on a world during that distant era, you would not witness a violent apocalypse. Instead, you would witness a slow, majestic, silent gravitational merger lasting hundreds of millions of years. The night sky of Earth would be rewritten into a breathtaking celestial ballet, glowing with colossal, winding rivers of billions of newborn stars stretching across the heavens as the tidal forces of gravity warp and reshape the two structures. Eventually, over billions of additional years, the Milky Way and Andromeda will completely lose their individual identities, merging into a single, massive, featureless elliptical galaxy that astronomers have already colloquially named Mokometa. Yet, as massive as this impending galactic collision will be, within the grand architecture of the cosmos, it is nothing more than a localized, insignificant event. It is a tiny splash in a small backyard pond. Because galaxies themselves do not exist in isolation, they gather together into even grander, more complex structural hierarchies. The supercluster hierarchy. The Milky Way and its roaring neighbor Andromeda belong to a localized cosmic family known as the local group. The local group is a gravitational cluster that contains more than 80 known galaxies, most of them smaller dwarf galaxies that orbit like satellites around the two dominant heavyweights, the Milky Way and Andromeda. This entire local collection of galaxies is spread across a region of space spanning roughly 10 million light-years in diameter. But if you zoom out further, you find that the local group is just a tiny, insignificant suburb inside an immensely larger cosmic metropolis. Our local group belongs to a vastly larger regional structure known as the Virgo supercluster. The Virgo supercluster is a massive concentration of galaxies that spans an astonishing 110 million light-years across. It contains at least 100 distinct galaxy clusters and groups, anchored at its center by the gargantuan Virgo cluster, a roaring, dense hive of thousands of galaxies that exerts an immense gravitational pull on everything in its vicinity. Our entire local group is being pulled through space toward the heart of this supercluster like a leaf caught in a slow, cosmic current. And yet, by the dawn of the 21st century, as astronomers began to construct the first comprehensive, three-dimensional maps of the deep universe, they discovered something even more staggering. The Virgo supercluster itself is not an independent structure. It is merely a small, peripheral branch, a single, minor appendage, of an even more gargantuan cosmic formation known as Laniakea, defined in 2014 by a team of cosmologists mapping the peculiar velocities of thousands of galaxies. Laniakea is an unfathomably immense supercluster structure. The name Laniakea translates to immeasurable heaven in the native Hawaiian language, a name that is both poetically beautiful and scientifically precise. First are the filaments. These are colossal, winding rivers of dark matter in galaxies that stretch across hundreds of millions of light-years. They are the highways of the universe, the densest regions of the grand macrocosm. Within these magnificent filaments, thousands of galaxies are packed tightly together, bound by the invisible shackles of gravity, constantly feeding matter into even larger structures. Where these immense filaments cross paths, they form nodes. Nodes are the glittering metropolis centers of the cosmic web. They are hyperdense cosmic hubs where thousands of galaxies converge into massive, boiling clusters. These nodes represent the absolute peaks of gravitational power in the universe, pulling matter from surrounding filaments over billions of years. But between these glowing filaments and dense nodes lies the second major component of the cosmic web, and perhaps the most terrifying feature of reality: cosmic voids. Cosmic voids are vast, unimaginably immense expanses of completely empty space that contain almost no galaxies, no stars, no dark matter, and virtually no atoms at all. They are the great deserts of the cosmos. A typical cosmic void spans anywhere from 100 million to 300 million light-years across. They are regions where the expansion of space has swept matter away, leaving behind a profound, pristine vacuum. Consider one of the most famous and chilling anomalies ever discovered by astronomers, the Boötes void. Discovered in 1981 by astronomer Robert Kirshner, the Boötes void is a colossal sphere of nothingness that spans roughly 330 million light-years in diameter. It is sometimes referred to by scientists as the Great Nothing. To understand the sheer scale of this emptiness, consider this: a region of space that size should, by all standard cosmological averages, contain at least 10,000 rich, glowing galaxies. If you were placed in a spacecraft right in the dead center of the Boötes void, the universe would appear to you as a terrifying, infinite abyss of absolute blackness. If you looked out the window in every direction, you would see nothing. No stars. No galaxies. No light. The nearest major galaxy would be tens of millions of light-years away, its faint light buried in the distance. Astronomers have remarked that if the Milky Way had been located inside the middle of the Boötes void, humanity would not have discovered the existence of other galaxies until the development of advanced telescopy in the late 20th century. We would have believed we were completely alone in an eternal, empty dark. Seeds of the Big Bang. How did the universe organize itself into this breathtaking, terrifying structure of filaments and voids? How did a chaotic explosion of energy grow into an intricate cosmic web? To find the answer, we must journey backward in time, all the way to the literal beginning of everything, the Big Bang. Immediately after the birth of our universe, approximately 13.8 billion years ago, the cosmos was a place of unimaginably extreme physics. It was a boiling, dense, uniform soup of pure radiation and subatomic particles. During this primordial era, there were no stars. There were no planets. There were no galaxies. The universe was so hot and dense that light itself could not travel through space. It was trapped in a continuous cycle of scattering off free electrons, creating a glowing, opaque, primordial fog. But this cosmic soup was not perfectly smooth. If it had been perfectly uniform, the universe today would be nothing more than a featureless, expanding cloud of cold gas. Instead, at the subatomic level, the universe was experiencing quantum fluctuations. According to the laws of quantum mechanics, empty space is never truly empty. It is a chaotic, boiling sea of energy where subatomic particles and fields constantly fluctuate, shifting in density from one micropoint to another. Then, a fraction of a second after the beginning of time, the universe underwent an event known as cosmic inflation. In an unimaginably brief moment, lasting far less than a trillionth of a second, the fabric of spacetime itself experienced an exponential, superluminal expansion. Space expanded faster than the speed of light, stretching the universe from a size smaller than a subatomic particle to a macroscopic scale. During this violent stretching of space, those microscopic, subatomic quantum fluctuations were instantly stretched across astronomical distances. The tiny, microscopic irregularities in the density of the early universe became frozen into the macroscopic structure of spacetime. They became macroscopic regions of space that were slightly denser, or slightly less dense, than the average surrounding soup. When inflation ended, leaving behind a vast, expanding universe, these frozen quantum seeds became the blueprints for all cosmic architecture. Regions that were just a fraction of a percent denser than their surroundings possessed a slightly stronger gravitational pull. Over billions of years, gravity acted as an amplifier. It pulled matter away from the less dense regions and dragged it into the denser pockets. The dense pockets grew into the first stars, the first galaxies, the first clusters, and eventually, the colossal filaments of the cosmic web. The regions that were less dense lost their matter entirely, emptying out over cosmic time to become the vast, silent expanses of the cosmic voids. We don't just know this theoretically, we have seen the photographic evidence. When modern satellites like the Planck Observatory mapped the cosmic microwave background, CMB, the oldest light in the universe, emitted when the cosmos was just 380,000 years old, they captured a relic snapshot of these very density fluctuations. The tiny temperature variations in the CMB, measuring just millionths of a degree, are the literal baby pictures of the cosmic web. Today, cosmologists can input these exact temperature fluctuations from the early universe into supercomputers, combine them with the laws of gravity and dark matter, and run advanced cosmological simulations. Over simulated billions of years, astronomers watch the computer screens in awe as the uniform primordial gas naturally organizes itself. The virtual matter begins to run along gravitational channels, emptying out of vast voids and clotting together into long, fibrous filaments. The simulations reproduce the exact structure of our observed cosmic web with jaw-dropping, mathematical precision. The universe literally grew from subatomic quantum whispers into a macrocosmic masterpiece. As gravity continued to sculpt the universe over its 13.8 billion year history, it produced individual structures inside the cosmic web that are so massive they challenge our very understanding of physics. One of the most controversial and jaw-dropping examples is a structure known as the Hercules Corona Borealis Great Wall. Discovered in 2013 through the mapping of gamma-ray bursts, the most violent, energetic explosions in the universe, the Hercules Corona Borealis Great Wall is a colossal, continuous filament of galaxies that stretches across an estimated 10 billion light-years of space. Take a moment to absorb that measurement. 10 billion light-years. The entire observable universe is roughly 13.8 billion years old. That means if you were to shine a beam of light from one absolute tip of this galactic wall, that light would have to travel through the vacuum of space for nearly the entire age of the universe just to reach the opposite side. It is a structure so enormously vast that it occupies a significant, measurable fraction of the entirety of the known cosmos. The existence of structures like the Hercules Corona Borealis Great Wall is deeply unsettling to cosmologists because it directly threatens one of the founding pillars of modern physics, the cosmological principle. The cosmological principle states that when you look at the universe on a sufficiently large scale, it should appear completely homogeneous and isotropic. In simple terms, it means that if you zoom out far enough, the universe should look roughly the same in every direction and at every location. There should be a structural limit, a point where the patterns of filaments and voids average out into a smooth, uniform cosmic distribution, much like how the individual threads of a canvas disappear when you step back from an oil painting. Cosmologists have mathematically calculated this limit, often called the end of greatness, to be around 1.2 billion light-years. No single, connected structure should be able to exist that is larger than this threshold, because the universe simply hasn't had enough time since the Big Bang for gravity to pull matter together across distances larger than that. Yet, the Hercules Corona Borealis Great Wall is nearly 10 times larger than this theoretical limit. Its sheer existence suggests that there may be patterns, forces, or structural anomalies in our universe that are vastly larger and more ancient than our current models of cosmology can comfortably explain. While astronomers continue to debate whether this wall is truly a single, physically bound gravitational structure or merely a statistical alignment of several smaller filaments from our earthly perspective, one terrifying reality remains absolutely clear. The universe contains organization and complexity on scales that defy our most foundational scientific expectations. The illusion of time and space. Everything we have discussed so far, from the solar system to Alpha Centauri, from the Milky Way to IC 1101, from Laniakea to the massive Hercules Corona Borealis Great Wall, exists inside a single, restricted domain of reality, the observable universe. To truly understand the scale of existence, we must now break through the illusion of what we can see and confront the nature of what lies beyond. The observable universe is defined by physics as the spherical region of space whose light has had enough time to travel through the void to reach our eyes and instruments since the moment of the Big Bang. We know that the universe is approximately 13.8 billion years old. Because of this fact, a very common, logical assumption is that the observable universe must therefore be a sphere with a radius of 13.8 billion light-years, stretching 27.6 billion light-years from one side to the other. It seems perfectly intuitive. If nothing can travel faster than the speed of light, and light has been traveling for 13.8 billion years, then we should only be able to see objects that are at a maximum physical distance of 13.8 billion light-years away. But the real answer is far stranger, more counterintuitive, and completely unmasks the dynamic nature of space-time. The actual diameter of our observable universe is not 27 billion light-years. It is approximately 93 billion light-years across. How can a universe that is only 13.8 billion years old contain light from objects that are currently 46 billion light-years away from us in every direction? The answer lies in a profound realization: space itself is expanding. Galaxies are not simply physical objects racing through a fixed, static, pre-existing room of empty space. Instead, the very fabric of space itself is stretching, expanding, and growing over time. To visualize this cosmic mechanism, cosmologists often point to a classic analogy. Imagine a loaf of raw raisin bread dough sitting on a counter, waiting to be baked. The individual raisins inside the dough represent galaxies, and the dough itself represents the fabric of empty space. As the dough bakes and rises, it expands uniformly in every direction. If you sit on one single raisin and look out at the other raisins, you will notice that every single one of them is moving away from you. The raisins that are farther away from you will appear to be moving away much faster than the ones close to you. But notice what is actually happening. The raisins themselves are not actively running or crawling through the dough. They are completely stationary relative to their immediate surroundings. It is the dough between the raisins that is stretching and expanding. The universe behaves in precisely this manner. As a photon of light leaves a distant, primordial galaxy and begins its long journey toward Earth, it must travel through space. But while that photon is mid-flight, racing through the vacuum at 300,000 kilometers per second, the space to which it is traveling continues to stretch and expand behind it and in front of it. By the time that ancient photon finally completes its multi-billion-year marathon and strikes the mirrors of the James Webb Space Telescope, the distant galaxy that originally emitted that light has been pushed vastly farther away by the continuous expansion of the intervening space. When cosmologists calculate the current, actual physical distance of those ancient galaxies, today a measurement known as comoving distance, they discover that the boundary of the furthest matter we can see has been stretched out to a radius of 46.5 billion light-years. Hence, our observable bubble is a gargantuan sphere spanning 93 billion light-years across, containing trillions of galaxies and boundless oceans of filaments. And yet, this entire 93 billion light-year arena is nothing more than a localized bubble. It is an arbitrary boundary dictated entirely by our specific location in space and the specific age of the universe. It is our cosmic horizon. And just like a horizon on Earth, it is an optical limit, not a physical wall. What lies beyond the 93 billion light-year edge of the observable universe? If you were to instantaneously teleport to a galaxy sitting right on the absolute outer edge of our observable bubble, 46 billion light-years away, what would you see? Would you look out into a physical wall? Would you see a cosmic cliff where space suddenly drops off into a meaningless abyss? The answer, according to the standard model of modern cosmology, is entirely profound. You would see more universe. If you stood on a galaxy at the edge of our horizon, you would find yourself at the literal center of your own, new observable universe. You would see the same cosmic web of filaments, nodes, and voids stretching out around you for billions of light-years in every direction. The universe does not stop where our vision fails. So, how far does this unobservable universe extend? Does it go on for trillions of light-years? Quadrillions? Or does it continue forever? To answer this, astronomers must measure the overall geometry of spacetime, a property known as cosmic curvature. According to Einstein's general theory of relativity, the mass and energy of the universe can warp and curve the fabric of spacetime itself. The universe could have one of three possible geometries. It could be closed like a sphere, open like a saddle, or completely flat. If the universe were closed like a sphere, it would be finite in size. If you traveled in a straight line for long enough, you would eventually loop all the way around and arrive right back where you started, much like how a ship sailing continuously west on Earth eventually returns to its home port. To determine the shape of space, satellites like Planck have meticulously measured the sizes of the fluctuations in the cosmic microwave background. If space were curved, those fluctuations would appear distorted or magnified through our telescopes. The results of these ultra-precise scientific measurements have consistently revealed something extraordinary. The geometry of our universe is remarkably, stunningly flat. The margin of error is less than a fraction of 1%. In the context of cosmology, flatness does not mean the universe is a two-dimensional sheet of paper. It means that Euclidean geometry applies across the entire cosmos. Parallel lines of light will remain perfectly parallel forever, never crossing and never diverging. And a flat universe carries a deeply staggering, mathematically unavoidable implication. If the universe is flat, and it has no boundaries, then it must be infinitely large. Let the reality of that concept break over your mind. An infinite universe. Not just big. Not just a very large number of light years. But a literal infinity. An endless, boundlessly repeating expanse of space, matter, and energy that continues in every direction without ever coming to a stop. No center. No edge. No beginning to space, and no end. Just an eternal, never-ending continuum of reality. If the universe is truly infinite, then we must confront implications that are deeply, profoundly disturbing to our sense of individuality and reality. In an infinite universe, the amount of space is limitless. However, the number of ways that subatomic particles can be physically arranged within any given volume of space is finite. Quantum mechanics dictates that a specific volume of space, such as our 93 billion light-year observable bubble, can only contain a finite, discrete number of quantum states, a finite configuration of atoms. When you pair an infinite amount of space with a finite number of possible atomic arrangements, a mathematical certainty emerges. Repetition becomes inevitable. This means that if you travel far enough out into the unobservable universe, past trillions and quadrillions of light years of space, you will eventually, mathematically encounter an identical copy of our observable universe. Somewhere out there in the infinite dark, there could exist another identical Earth, another identical solar system, a planet with the exact same history, the same oceans, the same continents, and the same cities. And on that distant, identical world, there could be an absolute, molecule-for-molecule copy of you, sitting in the exact same spot, listening to these exact same words, experiencing the exact same profound sense of existential vertigo. This is not a premise derived from science fiction or fantasy. It is the cold, unyielding arithmetic of infinity. If the universe is infinite, everything that is physically possible must occur, and it must occur an infinite number of times. The estimated distance you would have to travel to encounter an identical copy of yourself is a number so unimaginably large that it completely breaks human notation, one followed by more zeros than there are individual atoms inside our entire observable universe. Infinity strips away our uniqueness and replaces it with a dizzying, infinite hall of cosmic mirrors. But the mystery of our universe deepens even further. Because when we turn our eyes back to the 5% of the cosmos we can observe, we discover that everything we have ever seen, mapped, or touched is nothing more than an insignificant cosmic afterthought. For generations, scientists believed that the universe was composed entirely of the things we could see: stars, gas, dust, planets, and moons. We believed that matter was matter. But in the latter half of the 20th century, astrophysics suffered a profound crisis of reality. Today, modern cosmological measurements have confirmed that everything humanity has ever directly observed, every burning star, every spiraling galaxy, every black hole, every wandering comet, every blade of grass, and every human being who has ever lived accounts for only about 5% of the total mass and energy of the universe. The remaining 95% of reality is completely invisible, completely dark, and almost entirely unknown to us. The first invisible component is dark matter, which makes up roughly 27% of the cosmos. Dark matter does not emit, absorb, reflect, or scatter light or any other form of electromagnetic radiation. It is entirely invisible to our telescopes. We cannot see it, we cannot taste it, and we cannot touch it. Yet, we know it is there because of its immense gravitational footprint. In the 1970s, astronomer Vera Rubin studied the rotation curves of spiral galaxies and discovered something inexplicable. The stars at the outer edges of galaxies were orbiting just as fast as the stars near the dense galactic center. According to Newton's laws of gravity, this should be impossible. There is not enough visible matter in galaxies to hold them together. Based on the mass of the stars and gas alone, galaxies should be flying apart, flinging their stars out into the intergalactic void like water droplets flying off a spinning bicycle tire. Something unseen, something heavy, must be providing an immense amount of additional gravity to hold these galaxies together. Astronomers now know that every single galaxy in the universe is embedded inside an enormous, spherical halo of invisible dark matter. Dark matter acts as the invisible scaffolding of the cosmos. Without it, the cosmic web would never have formed. Dark matter provided the initial gravitational wells that pulled normal matter together in the early universe, allowing galaxies to be born in the first place. We are living inside an invisible architectural framework. But as mysterious as dark matter is, it is completely eclipsed by the final, dominant component of reality, dark energy. Dark energy accounts for an astonishing 68% of the universe. And its discovery in 1998 completely turned the world of physics upside down. For decades, astronomers assumed that the expansion of the universe must be slowing down. It made intuitive sense. All the matter and dark matter in the universe exerts an attractive gravitational pull, acting like a cosmic brake pedal that should be gradually slowing down the expansion that began with the Big Bang. But in 1998, two independent teams of astronomers studying distant Type Ia supernovae made a discovery that shocked the scientific community. The expansion of the universe is not slowing down. It is accelerating. Space is being pushed apart faster and faster with every passing second. Something is acting as a cosmic accelerator pedal, overpowering gravity on a macrocosmic scale and driving the universe outward at a manic, compounding rate. No one knows what dark energy truly is. It represents one of the greatest, most profound unsolved problems in all of modern science. The leading hypothesis is that dark energy is an intrinsic property of empty space itself, a concept known as the cosmological constant. According to quantum field theory, empty vacuum is never truly empty. It is a chaotic hive of quantum activity where virtual particles constantly pop into existence and disappear an instant later, generating a native, repulsive energy inherent to the fabric of spacetime. However, when physicists attempt to calculate the theoretical value of this vacuum energy using the laws of quantum mechanics, they arrive at a number that is 10 carat, 120 times larger than the actual value we observe through telescopes. This staggering discrepancy is widely considered the worst theoretical prediction in the entire history of physics, that we look out into a universe dominated by an invisible force that dictates the fate of spacetime, and our finest mathematical theories miss the mark by a number that defies comprehension. We are strangers in our own cosmos. Because dark energy dominates our universe, it does not merely govern the present, it dictates the absolute, unyielding chronology of the ultimate future. And that future is one of profound isolation and darkness. As this superluminal expansion takes hold, a tragic cosmological event will occur. One by one, distant galaxies will slip beyond our cosmic event horizon. The light they emit will no longer be able to bridge the widening gap between us, becoming permanently unreachable. Trillions of years from now, future civilizations living on worlds inside our local galactic remnant will look up at the night sky and see nothing but absolute blackness beyond their own local stellar neighborhood. The 2 trillion galaxies that currently illuminate our observable universe will have faded completely from view, pushed so far away by dark energy that their light will never again reach our coordinates. The ancient relics of the Big Bang, such as the cosmic microwave background, will be stretched out into radio waves so incredibly long that they will become completely undetectable. The evidence that the universe began with a Big Bang will vanish from the fabric of reality. Cosmology will become a completely impossible science. Future observers will live in a lonely, isolated island of stars, believing that they exist in a static, eternal, empty void, utterly unaware of the magnificent macrocosm that once flourished around them. Over the next few trillion years, galaxies will gradually exhaust the immense reservoirs of hydrogen and helium gas required to forge new generations of stars. The brilliant, high-mass blue stars will burn through their fuel in a few million years, exploding as brilliant supernovae and leaving behind cold stellar remnants. The medium-sized yellow stars, like our Sun, will swell into red giants and then fade away into quiet, cooling embers known as white dwarfs. The final bastions of light in the dying cosmos will be the red dwarfs. These are tiny, low-mass stars that burn through their nuclear fuel with extreme, hyper-efficient slowness. A single red dwarf can survive, quietly glowing in the dark, for up to 10 trillion to 20 trillion years, but eventually, even the longest-lived red dwarfs will consume the last of their hydrogen. They will go dark, one by one, like candles being snuffed out in a vast, dark cathedral. The stars of the universe will extinguish. By the year 10 carat, 14 years from now, 100 trillion years into the future, the stellar era of the universe will come to an absolute end. The cosmos will enter an incredibly long, cold epoch known as the degenerate era. During this grim era, the universe will be a cold, dark graveyard filled exclusively with stellar corpses, white dwarfs, neutron stars, and black holes. Occasionally, two dead white dwarfs will collide, sparking a brief, transient supernova that temporarily illuminates the dark, only for the shadows to quickly reclaim the space. If modern theories of physics are correct, even the solid matter of these stellar corpses may eventually disintegrate through a process known as proton decay. Over unfathomable timescales, the very atoms that make up the remnants of planets and dead stars will spontaneously decay, dissolving away into raw radiation. Matter itself is a temporary anomaly in the history of the cosmos. By the time the universe reaches 10 carat, 40 years into the future, all solid matter will have dissolved. The universe will enter the black hole era. During this unimaginable stretch of time, the only coherent objects left in existence will be black holes, from stellar mass remnants to the hypermassive monsters that once ruled the centers of galaxies. These black holes will dominate an empty, frozen empire, slowly swallowing up any stray particles drifting through the void. But even these titans are not immortal. Occasionally, one particle falls into the black hole while the other escapes out into space as radiation. This escaping particle carries away a tiny fraction of the black hole's mass. For a black hole with the mass of our Sun, it is a timescale that completely transcends human emotional processing. It is a duration so long that the entire 13.8 billion year history of our universe up to this point is reduced to a microscopic flash of lightning at the very beginning of a long, eternal night. One by one, over these unfathomable eons, the black holes of the universe will slowly wither away. As they reach the absolute end of their lifespans, they will finish their evaporation in a final, brilliant, violent flash of high-energy gamma radiation, releasing their last remaining energy out into the dark, and then, the final black hole will explode. With the final evaporation of the last black hole, the universe enters its ultimate, terminal evolutionary state, heat death, or the Big Freeze. It will expand into a thin, cold, uniform darkness where entropy, the measure of disorder in a closed system, approaches its absolute maximum possible state. In this state, there are no stars, no planets, no black holes, and no structures of any kind. The universe is nothing more than an impossibly vast, frozen vacuum filled with an incredibly dilute, low-energy soup of isolated photons, neutrinos, and occasional electrons drifting through space, separated by light-years of emptiness. The temperature of the cosmos will hover just a fraction of a degree above absolute zero. Because the universe will be completely uniform, with no differences in temperature or energy anywhere, no work can ever be performed. No information can be processed. No change can ever occur. Time itself becomes practically meaningless, because there are no events left to mark its passing. The universe is a cold, dead, featureless infinity, but even in this ultimate, eternal graveyard of heat-death, the story of reality may not be entirely finished according to the bizarre laws of thermodynamics and quantum mechanics. If you wait long enough, over timescales that defy standard mathematical notation, the vacuum of space can still experience random events. In a state of absolute heat-death, the universe can experience quantum fluctuation anomalies, numbers so large they represent the tower of exponents. Random quantum fluctuations in the empty vacuum could spontaneously cause a massive concentration of energy to materialize out of nothingness. A tiny, random quantum event could trigger a localized phase transition, sparking a sudden, violent period of cosmic inflation in a microscopic patch of space. It could trigger a new Big Bang, birthing a brand new, hot, dense baby universe that expands outward into its own pocket of spacetime, developing its own cosmic web, its own stars, its own galaxies, and its own biological consciousness. Our universe may simply be one link in an eternal, cyclical chain of cosmic births and deaths. Alternatively, we must confront a deeply terrifying possibility that could cut our universe's timeline short long before heat-death ever arrives: the theory of vacuum decay. In quantum physics, the fields that govern our universe seek their lowest, most stable energy configuration, a state known as the true vacuum. The Higgs field, which gives all elementary particles their mass, is currently believed to be in a highly stable state. But some advanced calculations in high-energy particle physics suggest that our universe might actually exist in a temporary, unstable state known as a false vacuum. Imagine a valley on a rugged mountain landscape. Our universe is sitting comfortably in a small bowl halfway up the mountain, believing it has reached the bottom. But further down the mountain lies a vastly deeper, more stable valley, the true vacuum. According to quantum mechanics, a phenomenon known as quantum tunneling could allow a tiny microscopic point in our universe to suddenly break through the energetic barrier and drop down into the true vacuum state. If this were to happen at any point in space, it would trigger a cataclysmic chain reaction. A bubble of true vacuum would form, and it would instantly begin to expand outward in every direction through the cosmos at the literal speed of light. Some bubbles might possess forces that prevent atoms from ever binding together, resulting in vast, eternal universes composed of nothing but lonely, isolated particles. And yet, across an infinite number of these cosmic bubbles, the laws of physics dialed themselves in with absolute, exquisite perfection. Stars forged heavy elements like carbon, iron, and oxygen deep inside their blinding nuclear cores. Ancient, violent supernova explosions scattered those heavy elements across the empty intergalactic void. Over billions of years, those drifting stardust atoms gathered together, condensing under gravity to form planets, oceans, cells, brains, and consciousness, which brings our long cosmic journey all the way back to you. Because despite everything we have explored tonight, Despite the 2 trillion galaxies, the terrifying emptiness of the Boötes void, the fibrous majesty of the cosmic web, the invisible scaffolding of dark matter, the accelerated driving force of dark energy, and the mind-numbing infinity of a potential multiverse, there is one fact that remains far stranger than all the rest. All of this immensity, all of these grand structural hierarchies and terrifying eons of time, is being conceptualized, mapped, analyzed, and understood by a small, 3-pound organ composed of fat and water sitting right inside your skull. The human brain is, as far as we know, the most complex arrangement of matter in the entire universe. It contains roughly 86 billion neurons, wired together into an intricate network of trillions of synaptic connections that bears a striking, uncanny structural resemblance to the cosmic web itself. Think about the profound poetry of that reality. The atoms that make up your eyes, your brain, your hands, and your consciousness were literally forged inside the hearts of ancient, dying stars billions of years ago. We are not separate from the universe, we are an intrinsic part of it. We are the stardust that has come alive. We are the cosmos evolved into a form that is capable of looking back at the stars, studying the equations of relativity, mapping the cosmic microwave background, and asking deep, fundamental questions about its own origin and ultimate destiny. The universe has developed a way to observe and know itself. Tonight, you are standing on a small, fragile, rocky world orbiting an ordinary star, nestled quietly in the arm of a single galaxy lost among trillions. You are suspended inside a reality so vast that human language begins to fail when trying to describe it. And yet somehow, against completely impossible cosmic odds, you are here. You are alive. You are aware. You are conscious. You get to look upward into the night sky and marvel at existence itself. The observable universe stretches for 93 billion light-years. Beyond it lies infinite space. Beyond that, perhaps infinite universes. And still, every single discovery humanity has made over our brief history represents only the very beginning of our journey, because the deeper we look into the dark cosmos, the more the universe seems to whisper the exact same message to us over and over again. You are smaller than you can possibly imagine. And existence is larger than you can possibly comprehend. But for one brief, magnificent moment in cosmic history, you get to witness it. And that may be the rarest, most beautiful thing in the entire universe. Good night.